Hello, this video is on the rate of change. And to talk about it, let's remind ourselves about the similar concepts that we discussed back when we were talking about the definition of the limit and the definition of the derivative. And that was the difference between the average velocity and the instantaneous velocity. So remember, if s of t is representing your position as a function of time, then the velocity denoted average velocity over an interval t0 to t1 was in shorthand just change in velocity, change in position all over change in time, and in long form would be s at t1 minus s at t naught all over t1 minus t naught. So that was the average velocity over that time interval. And there was a picture that went along with it. Remember, if you were to graph as a function of time your position, say it looked like this, and you put t0 here and t1 here, then if you connected these 2 points, made a triangle this way, then this distance here was the change in time, this distance was the change in s, and the slope of that secant line was actually geometrically what that average velocity was. And then we also had instantaneous velocity. So remember, velocity, often we just called it velocity, but the instantaneous velocity was the limit as delta t went to 0 of the change in position over the change in time. And more precisely, now that we know about derivatives, remember this is just exactly s prime at t naught. So the derivative was the instantaneous velocity. And it had a picture as well. If you were to graph, again, your position function against time and put t naught here, then you would draw the tangent line to the graph, and the slope of this line is exactly, remember, what geometrically the derivative was. All right, that worked for position, but in fact we can do this with any function. It's just we don't call it velocity, average, or instantaneous anymore. We just call them rates of change. So for a general function f of x, the average rate of change of a function f of x over some interval x0 to x1 is just shorthand the change in f all over the change in x. In long form, f of x1 minus f of x0 all over x1 minus x0. So that looks just like the picture we had with velocity, except it makes sense for any function. And there's a picture that goes with it, as we've seen before, except now you graph the function f of x, and if you have x0 here and x1 here, then you can draw this triangle underneath, where this is the change in x, this is the change in f, and then the slope of that secant line is geometrically what's being calculated here. Okay? So that's the average rate of change. And there is, of course, a instantaneous rate of change. So the rate of change of f of x at x0. Now, often people don't say the word instantaneous, but I'll add it in here. They really mean the instantaneous rate of change, but they usually just call it the rate of change, is the limit of that average rate of change. So the limit as delta x goes to 0 of the change in f over the change of x. This, of course, is just the derivative. So that's f prime at x naught. And there's a picture, just as before, with tangent lines. So if you graph the function f of x here, and you suppose x naught is here, come up here and draw the tangent line, then the slope of this tangent line is geometrically what is being calculated by the instantaneous rate of change. We'll do some examples in the next slide, but that's all it is. See ya.